recent observation at LIGO. When we organized the FTAC conference, we had no idea that we would be faced with this enormous news, this one of the two biggest discoveries of this century, which is 16 years old already. And of course, this is one of the biggest experiments currently running in the world. We had no idea we would have something out of one of those things. And it turned out, because it was so close to the conference, we wanted somebody to speak about it. And it turned out that all the Indian members of the LIGO team had already said no about coming here. Because we had already invited them for FTAC and they had already said no. So when we contacted them again, they said, no, we're too busy, we cannot come. And of course, they're too busy. We all know where they are too busy. They're all talking to the ministers about getting another branch of LIGO in India. Now we were lucky, very lucky actually, that Professor Bishop was visiting Naresh at that time, and he actually agreed to come to FTAC even without a prior invitation. And he kindly agreed to give a talk on the gravitational wave detection event, and he is a renowned expert on the gravitational waves. Professor Bishop did his first degree from Cambridge and his PhD from Southampton, and he has been working on gravitational waves for 25 years now, actually more than that. And he'll be talking about the recent gravitational wave event GW150914. Professor Bishop.
Okay, good afternoon everybody, and thank you for the invitation. So, the way I'm going to present this talk is, first of all, I'll start off with a very basic introduction to gravitational waves, because I'm not sure how many people are completely familiar with them. So how do we do? So the first slide shows, suppose a gravitational wave is going into the screen and there's a ring of particles. Right, what will the effect of the gravitational wave be? So what it is it stretches the ring in one direction, then the other direction. Okay, and this is the effect that LIGO is trying to measure. The effect is enormously tinier than is shown in that animation. I mean, the effect is around about 10 to the minus 21, 10 to the minus 22. Okay, but that's the effect that one's trying to measure. So the important thing to understand about gravitational waves is that the action of the wave is transverse to the direction of motion. So if the wave is going into the screen, the effect is acting within the screen. Okay, and a gravitational wave moving in this direction has no effect this way. The next issue to look at very briefly is how LIGO works. So what we have is a laser source, a beam splitter, two high vacuum tubes, each 4 kilometers long, with mirrors at either end. Right, and then the light goes through and reflects back and forth a number of times. So you put in a laser source at around about 20 watts, and the power circulating is around about 100 kilowatts. So the light's going back and forth many times. So the effect of that is to magnify the length of the arms. Okay, then it comes back through the signal recycling to the photodetector. Okay, and then the effect that one looks for is any interference. Okay, it will be set up so that if there's no wave, there is complete interference, or actually you wouldn't see anything except noise. And then what you do see, it should be the signal. There are currently 2 detectors operating, one L1 in Louisiana and one in Hanford, Washington State. And what's going to be important a bit later is the light travel time between the two of them is 10 milliseconds. The LIGO detector is sensitive to gravitational waves within a certain frequency band. It's, as a broad rule of thumb, right, because we have to expand this out, the effect of these mirrors is that these arms are actually somewhat longer. But the size of the detector gives you an order of magnitude of the wavelength that you can detect. Right, and what this translates to is that LIGO is sort of sensitive from round about, so this is the design sensitivity curve. This is not the actual sensitivity reached yet. So LIGO is sensitive from somewhere between about 20 hertz up to a little over 1,000 hertz. All right, with peak sensitivity around about 200 hertz. Right, and then what sort of event does LIGO see? Okay, so what we've got here is 2 objects in circular orbit around each other. I'll talk about this case because that's really the simplest to describe, and it brings out all the features. Okay, and what? So the frequency of the wave is, well, if you take the orbital period and multiply by the orbital frequency multiplied by 2, you get the wave frequency. The amplitude of the wave is determined by essentially the rate of change of the mass distribution. So what you want for a large amplitude is large masses at high speed. Okay, and the highest speed you can get in relativity is the speed of light, or nearest that. And the largest sort of masses you can get are 2 black holes. So the most powerful source, and then 2 black holes as they spiral in towards each other, are moving very fast, nearly at the speed of light just before merger. So that's the most powerful source that you will get. Anything else is somewhat low, or significantly low. All right, so in preparing this talk, the papers that I've looked at are first of all the LIGO report, which I suspect many people have seen. Then a more detailed report which appeared on the archive. I actually got just slightly after the initial article. And then there are 2 other articles that are because there's evidence of a gamma ray burst at the same time, and that's significant in interpreting the physics and the astrophysics. All right, so first, the way I'll present this talk is first of all the observation of the event, then what I might call a heuristic or basic interpretation, without going into any computers or anything. You can just look at that waveform and say what it is, and I'll really show you how you do that. Then a little bit about the gravitational waveforms and the binary black hole parameter space and how they vary, the different type of waveforms that you can get. Then actually doing the source parameter estimate. So this will be an approximate source parameter estimation. This is an accurate source parameter estimation. Then talking about the Fermi observation of this gamma, which is the gamma ray burst monitor, also observed a transient at the same time. The implications for physics and astrophysics, and then conclusion. So again, this is something that I'm sure many people have seen before. This is the diagram that appeared in the news conference and is in that physical review letter. So on the top we have the raw data. This, first of all, in Washington and then in Livingston. And then what we do is also in this diagram we shift H1 by 6.9 milliseconds. All right, and so one can see that they are more or less coincident. All right, and then this is which will end up producing or discussing is the calculated waveform with the estimated source parameters that best match the data, and then one can see that they do look approximately the same. Right, now in order to start talking about just doing some basic interpretation, I mean the key sort of diagram is this one here, this frequency amplitude diagram. All right, so what we see is that there's a peak frequency around about 256 hertz, and that this sort of event goes for about 1 to 1.5 milliseconds, or 0.1 to 0.15 seconds. Right, so the basic interpretation would go like this, which you can just, once you've worked with this stuff, you can just look at these things and say this. There's a ring down at about 256 hertz, assuming the ring down is the lowest quasi-normal mode of a Schwarzschild black hole. You just put in the period t is 2 pi over 0.37. 2 pi m over 0.37. This gives you a mass of about 50 solar masses. That just comes from the order of magnitude of the peak frequency. What you can also do is apply the Chirp mass formula, which gets slightly more complicated. But what you can measure is the frequency and the rate of change of it. And then all right, so what you can, the Chirp mass in terms of the masses of the of the two components is this, and then given in terms of the frequency is that, which you can then, when you work that all out, it works out to be about 30 solar masses. Right, translating that into M1 plus M2, this M1 plus M2 will be at a minimum when M1 equals M2. And you get out 69 solar masses. So the radius of each object is at least 105 kilometers. Further, the frequency at maximum intensity is 150 hertz, corresponding to an orbital frequency of 75 hertz. So the objects are no more than 350 kilometers apart. All right, the objects must be of approximately equal mass, because otherwise the total mass would be inconsistent with the ring down mass. So, I mean, for example, if M1 equals 10 M2, then you'd have M1 plus M2 is 127 solar masses. So this immediately, I mean, just by looking at this, fixes it that you're talking about two approximately equal black holes. I mean, they're black holes because I mean, we've got a distance between the centers of, say, 350 kilometers, and the radius, length of the radii of the object, that's 200 kilometers. There's only 100 or so kilometers, 150 kilometers left. It's a very compact object. All right, now let's start talking a little bit about the waveforms that you can get from different scenarios. So this is a scenario of M1 over M2 equals 6, a substantial spin S1, a moderate spin on the other one. And you get these features here, and which is somewhat different to what you saw. It's different in sort of two ways. The first way is that you get lots of cycles before you get this final merge. Okay. You can understand that physically because you've got a lot of angular momentum that has to be lost. With all this angular momentum, the system can't form a black hole, otherwise it would have A greater than 1. So it's going to radiate it away. So a number of cycles are spent just radiating it away. The other difference you see is you get these sort of, you get in the previous diagram, if you were to plot an amplitude time curve, it would look something like that. It's monotonic increasing. In this case, it's jerking around. Right. And that's a sign of precession, which is due to having off-axis spin. If the spin is aligned with the orbital angular momentum, you won't get this effect. But if you have your components in the orthogonal to the orbital angular momentum, you start getting this precession and this jerkiness. Okay, so what we can, okay, so then neither feature is apparent in this data, so one doing the analysis, one can focus on waveforms from non-spinning black holes. Or at least certainly non-spinning well, we will actually allow for some on-axis spin, but not off-axis spin, which makes the whole parameter space a lot bigger and more complicated. Secondly, this plot shows you the blue line is when M1 over the total mass in both cases is the same, is 1, but in the blue line is when for two equal masses, and the orange or the red line is when M1 over M2 equals 8. So what we see here is, looking at this, that they sort of look similar. In both cases you're getting increasing amplitude and increasing frequency. Alright, but one of them is about half or less the size of the other one. Alright, so you might think, well, alright, the way to distinguish them is from the size, but unfortunately that doesn't work. Because in order to know the amplitude that we'd expect, we need to know how far away the object is, and that's one of the things we want to measure. So there's, alright, so we can't just go straight from the amplitude to determine the mass ratio. We have to do it some other way. All right. How should the effects? So, the way we'll actually do it, I'll come to later. But what I just want to show you is that although the waveforms look similar, when you analyze them in terms of frequency against time and amplitude against time, they're not. So, I mean, in both cases, the frequency against time, it's really to do with how it peaks. The high mass ratio one peaks at a noticeably different level than the equal mass case. And the amplitude peaks also, it's higher in the equal mass case than the non-equal mass case. Now, I'm not going to go through the analysis of that because that's, I mean, not how it's done, but just to show you that even though the curves look the same, they're not. And so you can expect to pull out these differences to be, in order to distinguish what the source is at, what source we're actually seeing. So the actual source parameter estimation is done in the following sort of way. First, we construct a template bank black hole merger waveforms over the 3D parameter space, where S1, S2 spins aligned with the orbital axis. Right. And then we construct the mismatch between the calculated waveform and the observed waveform. So the mismatch is 1 minus this inner product. And there are different ways of defining that inner product. But essentially what it is it's normally evaluated in the Fourier domain. It includes the detector response function. Because if there's a mismatch at some frequency where the detector's not sensitive, that doesn't matter. All right, and it's important to weight the mismatch at frequencies where the detector's more sensitive than at others. So what we're doing is we're comparing the calculated waveform and the observed waveform. And there are tens of thousands of these waveforms in the template bank. Right, so what we want to do is to have an inner product that satisfies, so it has to be positive and between 0 and 1. And we want it to be 1 if and only if H1 is a constant times H2. And then you put it in the computer and say minimize over the template bank and see what the answer is. All right, so these are the results that come out. So you pick out the best model and then you do some statistical analysis as well to find out models that fit in a way to within 90%. And this is what you obtain, that M1 is 36, then plus 5 or minus 4 solar masses. S1 is just restricted to be less than 0.7. So, I mean, there's no estimation beyond that, so what that's really, I mean, essentially you can regard this as a Schwarzschild black hole. M2 is a little bit smaller. There's no restriction on S2. The final mass is 62 plus or minus 4 solar masses. And the final spin you can pull out as 0.67. That means that the system has lost 3 solar masses during about less than 0.1 of a second, somewhat less than that. So you can think of the peak luminosity actually works out at around about 200 solar masses per second. That in terms of power output is enormous. I mean, it means our sun will have a lifetime of what, about 10 billion years, and during that time, due to nuclear fusion, it will lose about 5% of its mass. Right, so it's the whole of that times 20 times 200. It's absolutely enormous, the power output that's occurred. All right. so the next thing we can do is, yes, these figures for M final and S final were not made using by modelling the quasi-normal modes. They were used from the models that gave the best fit to the data, and what were their M final and M final. So one check one can look at is, for these values, the quasi-normal mode parameters are a decay time of 4 milliseconds and a frequency of 251 Hertz. Right, all right, where the amplitude is going, so this decay time is, we've got this exponential decay, that's just the characteristic time. So now we use the observed data with the delay shown after peak amplitude to estimate the quasi-normal mode directly and plot those and these parameters on the same curve. So what you get is the black line is the parameters that come from the model fitting. Right, so what it depends with the data is you take the peak and you've got to decide how long you're going to wait after the peak before you start measuring the quasi-normal mode. Because after the peak, I mean, a quasi-normal mode is a linear vibration, all right, whereas immediately after you're definitely not linear. All right, so you've got to decide how long to wait. So waiting 1 millisecond you'll get, and if you were to, you get that. Waiting 3 milliseconds, you get this curve here. 5 milliseconds, you get that curve there, and then 7 milliseconds, you get this curve. All right, so what we see is that if you wait 5 milliseconds before you start measuring the quasi-normal mode from the data, what you find is that the reconstructed model is more or less exactly in the center of the estimate that you get, so that you can say they're certainly consistent. All right, the one thing you might have noticed that I haven't talked about in the estimation results is the distance, because that's the most difficult issue, and that we need to talk about a little bit. All right. The distance is a problem because there are certain unknowns. Okay, and what it's to do with is, I'm going to try and demonstrate something in 2 dimensions, and my drawing drawing 3 dimensions in 2 dimensions is difficult. All right, so let's suppose that one LIGO is there and the other one is over there. Okay. All right, so what we've got is, and LIGOs doesn't give us any information. A single LIGO detector gives us no information about the direction. Okay, so suppose that the wave came straight down like that. All right, then the wave would act orthogonally to the direction, and if LIGO 1 is here and LIGO 2 is over there, we will have the arms in the plane orthogonal to the direction, so the wave will have its full effect. Okay. Now, and it would have its full effect over here as well. All right, and in that case, I mean, which is not what was measured, what you would find is that the time delay between H and L would be 0. Okay, because the wavefront would hit both detectors at the same time. All right, but that would not tell you that you've got a wave that's orthonormal to the planes of both detectors, because the wave propagation direction could be anything like this. Okay, so in fact you'd have an uncertainty over 360 degrees. Okay, so although when the wave comes full down here, you're at max, the calculated waveform is equal to the measured waveform. If it's coming here, I mean, one arm of the detector is going to see nothing. Okay? The other arm of the detector will see things. So what that means is that your measured field is only half of the the field as it would be if you had a detector orthogonal to the direction. And what the what the models give you is the field as though the wave were orthogonal to the plane in which the detectors are. Okay. Now, if on the other hand the wave was coming in this direction, right, the delay between one and the other would be 10 milliseconds. Okay, because we'd go the full light travel time. All right, you'd have no ambiguity about the direction of the wave. Okay, there's no ambiguity. If it's going in this direction, there's no ambiguity. Right, but what you would have is that, again, you'd have this half factor. Right, now in this case what we've got is that we know that the time between the H and L is 6.9 milliseconds. Right, so we can take this wavefront here, draw a right angled triangle. One side is 10 milliseconds, one side is 6.9 milliseconds. We divide 6.9 by 10, which is easy, take 0.69, and then just say arc cos of that, and we get out an angle. Okay. So what that tells us is that we've got the wave that's somewhere restricted within a cone like this. Right, so it's not as easy as having factors of 1 or 2. You end up with some trigonometric formulas, which I'm not going to write down. Okay. But I mean, you can then work out a maximum and a minimum. Okay. In the same sense as the variation is going to be less than the factor of 2, but it's going to be governed by some sine and cosine. All right, so the wave direction, yes, so I actually worked it out, was 47 degrees away from the vector LH. Okay. Right, if however indigo had been operating, that problem wouldn't arise. Okay, because with 3 detectors, I mean, there are 2 reasons to have 3 detectors. I mean, one is source localization, so you can try and search for an electromagnetic counterpart. But the other is to remove this degeneracy in the magnitude of the wave in the TT gauge. Right, but that's just one of the problems that we've got concerning the distance. The other problem is this: the angle between the direction of propagation and the orbital axis is unknown. So let's just go back to. Right, suppose that LIGO is over here somewhere and is looking at that head on. Right, then you can work out the gravitational wave field. Now instead, suppose that we're looking at the system edge on, so I'm over here. There's going to be a factor of 2 difference between the two, between the magnitude of the waveforms that will be observed here. Okay, so one has that. There are possible, we can't do it for this case, there are possible ways to resolve that degeneracy if the signal had been much more powerful, because then one can pick out the higher order modes, and the relationship between one mode and the other gives you an indication of that angle, the angle by which you're observing it away from the polar axis. Okay, but in this case we can't do it. So that degeneracy is always going to be. All right, so putting the 2 effects together, that's why there's such an uncertainty in the distance of the event. I mean, what you see, everybody tends to say is 430 mega, is it 440 megaparsecs, no, 400 megaparsecs away. but there's actually a large uncertainty in it. Okay, and it's because of those two effects. Another fascinating event is the gamma burst monitor recorded a transient at this, well, 0.4 seconds after after the gravitational wave event, lasting for 1 second. All right, so then the question is, are the two events related? All right. There are two papers which I put up at the beginning which investigate this. And it amounts to a very careful analysis of the data and the type of random events that one can get. And one certainly does get random events. All right, but you're talking about a sort of random event that could be confused with a measured event of about 1 event per day. Okay. Now, then you do some various statistical calculations, but essentially what it comes down to is that the order of 1 second over a day is a small probability. And so the estimated probability that it's physically associated is 0.998. So the event would I mean, this is in a way unexpected because with neutron stars you would certainly expect there to be a gamma burst event associated with it because it's the matter that produces the gamma ray burst. All right, in this case it depends on the environment where the black holes are, whether one could have an environment where there's very little other matter around, they're just two black holes, they're going to merge and there's going to be no electromagnetic counterpart at all. Because the electromagnetic counterparts can only come about if there's some matter somehow to be excited. So what it does is it implies that it happened within a moderately dense medium. Dense doesn't necessarily mean that it's gaseous. I mean, it can be that it's within a globular cluster or something like that, and so the black holes are continually disrupting stars, and from the stars forming accretion disks. The difficulty is that there's very little. The detailed modelling of this is highly uncertain. It's very speculative. Okay. But the sort of thing that has been done, all one can say is the delay and duration are not unexpected. So it's possible. It's the sort of thing that could be consistent with theories that have been done, but I mean it's a highly uncertain area. But I mean, the interesting thing is that probability, which has really nothing to do with that. That's just a statistical probability based on the time of the event. Right, now, I finished this talk last night, and then this morning Naresh told me about two papers which present alternative views, which had just appeared on the archive this morning. Okay, Naresh obviously gets up early to look at the...
I don't know what.
Okay, so I had a look at these two papers, and the first one is the gravitational wave bring down a probe of the event horizon, and argues that there's insufficient detail in the ring down to say that it's definitely showing a ring, definitely showing an event horizon. And if one goes back and looks at this diagram here, I mean, one can say that that's true. Right, this is actually allowing a fairly wide ranging in parameter space. Okay, so I would regard that as a valid comment. That certainly there could be other theories which would not necessarily have event horizons which could produce some data. All right. This paper says he doesn't believe that GBM signal is related to the gravitational wave signal. The argument is basically astrophysical. It comes down to this is outside my area, so all I can say, I mean, essentially what he's saying is that he can't think of the astrophysical circumstances that would produce that outburst he regards as unlikely. Okay. How correct that is or not, I can't say. Okay, but I mean, one should be aware of these things. And I'm sure there are going to be lots of other papers like this in the near future. Actually, sort of in a way, perhaps it's surprising one's only seen them now. Okay, so what are the implications for physics? So if the Fermi observation is physically associated, what it tells us is that the speed of light and the gravitational waves are essentially the same. All right, down to, with a maximum difference of about 1 part in 10 to the 17, which is just 0.4 seconds over 1.2 times 10 to the 9. There are papers written on this, but I mean, it's just one divided by the other. Okay, acting purely on the LIGO data, it shows no dispersion, implying that gravitons in different frequencies, at least in this range, 50 to 250 hertz, travel at the same speed. This implies that the quantum wavelength of the graviton is at least 10 to the 13 kilometers. Inclusion of the Fermi data improves the down to 2 times 10 to the 17 kilometers. So it's coming down to how massless is the graviton. The consistency between the observed and predicted waveforms amounts to a test of general relativity in the strong field regime, but really there's been no quantification of this. And in a way, this is probably an area that needs to be looked at, to be able, because what we've got so far is things like the PPN formalism, which talks about, in a way, deviations from Newtonian theory. And one can be precise as to how much one theory differs by another, and then you measure it. And the strong field regime, which is difficult to do, because what do you measure about? That there's nothing, and this is perhaps something. This is going to become an issue for the future that one needs to think about. Implications for astrophysics. Well, the first implication is just that intermediate mass black holes exist, and that's interesting in itself, because the end state of a star has not been expected to lead to a black hole more massive than about 10 solar masses in terms of the usual stellar collapse scenarios and of the black holes that have been measured in our galaxy. The observed black holes could have arisen through prior mergers or some other astrophysical process, and there are going to be lots of papers about this in the near future, I'm sure. Okay, the fact that these things exist is by itself interesting, even if it's just 2 of them. As more events are observed, it will be possible to estimate black hole and neutron star populations over various masses. It's unrealistic to do statistics based on one observation, although people try to do so. I think what you can say is that the detection event is not unexpected in terms of current astrophysical estimates of the frequencies of such events, which are over a very wide range. So I think that you can say that it's not inconsistent. It's not a great surprise that we've seen something. Right, but once we start seeing more of them, we can then talk about populations and event rates, etc. Okay, so to conclude,
well,
It was actually 100 years ago, in 1916, that Einstein wrote a paper showing that gravitational waves are a consequence of GR. Although at the time he believed that the prediction was untested. And in terms of the technology and knowledge of astrophysics at the time, that was true. The theory developed, and the first experiments were conducted in the 1960s by Joseph Weaver using resonant bars. And there's really been a continual interest and slow development in both the theory leading to the design of laser interferometers, which was eventually adopted in the 1990s as something that was feasible and should be built. And in 2002, the first LIGO went into operation. All right, so the enormous effort to detect gravitational waves has paid off. This result has been achieved by the cumulative work of many thousands of people in a huge variety of disciplines. Engineering, experimental physics, material science, statistics, data analysis, computer science, analytical and numerical relativity. How the experimental physicists measure a distance of 10 to the minus 22 centimeters. No, ratio of 10 to the minus 22 that is amazing. So we're now in the age of gravitational wave astronomy. Within a few years we should have precise information about astrophysics, populations of black holes, neutron-star binaries, core bounds in a supernova explosion, so the details as to what happens in a supernova explosion in terms of mass movement, as well as information about the equation of state of a neutron star. We'll be able to test gravitation theory in the dynamical, strong field regime. This will lead results about the validity of GR and other theories. It can even be hoped that experiment will provide a clue needed to unify gravitation and quantum mechanics, which, what one really wants is some form of discrepancy that can only be explained by some form of quantum effect. Okay, that's way for the future, but that one can hope for. But as we open a new window onto the universe, we shouldn't be surprised to observe something totally unexpected. Thank you.
Questions?
The Chirp formula that you
Yes.
that formula is derived from the first. The Chirp formula is derived from the first or the second post-Newtonian approximation, if I'm not mistaken, right?
Yes.
Now, like you pointed out correctly, it's not clear if that formula should hold in the background of black holes, merging black holes.
No, but it's yes, it's true. That formula is based on an approximation, and it doesn't matter whether you're talking about black holes or any other objects. If they're a long way apart, it would certainly hold. So, and as they become closer and closer together, yes, there will be deviations. Certainly at merger there will be deviations, and in order to, but this sort of thing is used more to provide what you might call a first estimate. The actual source parameter estimation has come from detailed numerical modeling. And actually in this case, the Chirp formula works pretty well, because it gave a total mass of 69, and the actual mass from the was 65. So it worked. Yeah. So the actual mass was around about 65, and the Chirp formula gave us 69. It was just meant to give a sort of order of magnitude estimate. And for that, it seems to work reasonably well.
I have a question.
Yes.
You wrote that strain, which is delta L by L, is 10 to the power minus 21. That means delta L is 10 to the power minus 3 times per millimeter. That means 1,000 of a proton radius.
Yes.
I just wanted to know your opinion. How do they measure this such 10 to the power minus 3 times 1 fermimeter proton radius? I mean, that's amazing.
Yes. Yeah, that is...
How do they do it? No, I mean, it's just 4 kilometers.
Yeah, it's not quite 4 kilometers. This is going back and forth probably 1,000 times. That gives you another. So that gives you a 10 to the 3. And that, the rest of it, I do not understand. I do not understand. I'm not the person to answer that. But I'm also amazed by it.
One of the remark made is we cannot claim it to be a black hole. Is that correct criticism?
So what we can say is that the model in general relativity of 2 black holes fits very well. I mean, that's what we can say. What we can say is that it's 2 highly compact objects,
Yes.
resulting in a third highly compact object. Within general relativity, that can only be black holes. Within some other theory,
So in atomic physics it happens, no? Electron and proton hold modular atom. Electron spirals around to spirals down to the proton. Looks like what you're doing is inspiring
yeah,
The 3 states.
and radiating, no?
yes,
That need not, why is that black hole? In fact, how will you see horizons? Even horizon cannot be seen.
No, you don't see
Quasi-normal
horizon.
modes which you
Yeah.
find from here.
Yeah.
How do you distinguish quasi-normal mode of a black hole from that of a very in
terms of, okay, so let me, in terms of the data given here, the data observed here, you can't. Now, if the data was, if the signal was 10 or 100 times more powerful, you would then see not just, you would then look not just for the lowest order quasi-normal mode, but the others. Right, and then I would think that you have, then it becomes, the case becomes stronger and stronger. Okay, but at the moment, yes, I'd agree. The quasi-normal mode data is, you can just look at that. It's not very clear.
Yes.
All this mass estimation is by simulation, or
Sorry?
the mass estimation is by simulation?
Yes.
Simulation?
It's based on, you take this huge template bank of solutions and look and work out the whole waveform, match it against the data, and look for the best fit.
Now,
Patrick,
can I?
okay. He's been waiting to ask questions.
Okay, regarding this estimating the mass parameters, since the binary black hole could be having a Doppler shape, as well as if it is in an external galaxy, there is also a cosmological redshift. Since the redshift information, both Doppler as well as cosmological redshift is unknown, probably the uncertainty is coming in the mass estimation. Because we don't know whether the binary system is moving towards us or away from us. That is one uncertainty. Similarly, it's a greater than 350 megaparsec away. So there is a cosmological redshift also.
Yes. So I should add perhaps that this data is, these estimates assume standard cosmology. So once you've got an idea as to the distance, you can then work out the redshift from that distance and put the whole thing together. So that you can do, but it's certainly true that one's assuming standard cosmology and that there's no peculiar velocity of this system with respect to the cosmological flow.
Yeah, so redshift has been set to 0, but the wavelength will also change. Apart from the
Yes.
distance uncertainty,
No,
the
yes.
redshift will also affect the wavelengths.
Yeah, but that's all taken into account. Okay, but so that's taken into account. What isn't taken into account is any peculiar motion of the system.
How sure are we about this gamma ray burst? In coincidence, how sure are we about the gamma ray burst along with this gravitational wave event? In say how far it can be from the event, or how much the angular difference between them?
All right, so let me a little bit more about the gamma ray burst. If you look at, yeah, this paper here. Okay, that. The trouble is that both LIGO and gamma ray burst are not particularly positionally sensitive. All right, but I mean, even so, I mean, I haven't got this paper. I mean, it produces a diagram. All right, LIGO's got from LIGO alone, you get an uncertainty as to the position over 600 square degrees. The uncertainty with the gamma ray burst is actually somewhat larger, but I mean it's nothing like. In neither case are you talking about the whole sky. I mean I don't remember the figure, but it's probably something like 1,000 square degrees, and there's a significant overlap between the two. So I mean it's not as though LIGO's saying the event's over there and the gamma ray burst is saying it's over there. They're not saying they're both in that direction, but they're both in sort of similar directions.
But are we sure the distances of each one of them?
We've got no idea about the distance of the gamma ray burst.
Then how do they estimate the light, the gamma ray burst is the light thing, arrival time, and the gravitational wave arrival time. You mentioned some time difference.
No, okay, sure. No, I mean, that's true. We know the arrival time of the gravitational wave event at Livingston and Hanford.
Yes.
I mean, down to the millisecond.
Yes.
We know the time of the gamma ray burst event was measured by Fermi with a clock on
Yes.
that satellite.
But we don't know where it started.
We have no idea where. No, we don't know where it started. We do have these estimates as to the distance, something like between 230 and 570 megaparsecs.
Right.
So what we can say is it's travelled at least 230 megaparsecs, and the difference in times is around about half a second. So that gives you an estimate as to the difference in speeds.
Is that good enough to make that both of them travel with the same velocity?
Well, the same the velocity to within 1 part in 10 to the 17 or something like that. Yes.
That accuracy seems to be quite high.
It's the. You take 1 billion years, which is 10 to the 9 years. There are 30 million seconds in a year. That gives you 10 to the 16. and you take half a second or so. You just, it works out at about, I mean, I've just, whether it's 10 to the minus 17 or 10 to the minus 16, I haven't checked, but in order of magnitude, it looks right.
No, I am just coming to say, you see, this event was,
You have to turn it on, I think.
yeah, this event was detected in last September.
Yes.
And since then, there has been a rumor all around. And so, my colleagues in Ayuka, those who are involved in the LIGO project, so they have been working on their calculation. So now, you see that you have this 47-degree,
Yes.
and that's Nigel mentioned what would have happened if LIGO was working. There was a third detector in Indigo. So if Indigo was there,
Yes.
that 47-degree reduces to 4 degrees.
Yes.
So that's the thing. That would have been something.
And Modi has been told that.
Well, we tried
Yes,
to
I said the money.
we tried to.
You didn't tell before.
Oh, yeah. Not to Modi, we tried to dress up everything much more good.
I had a question about, follow-up question of, question asked about GRB. The GRBs, of course, have been observed, quite a few have been observed so far.
Yes.
I have no idea, I'm not an experimentalist. Do they measure intensity or number of photons received? I mean, I'm just curious. This is an event, from the gravity point of view, is the first time you observe such an event. But the corresponding gamma ray burst, is this of certain exceptionally high magnitude, or is it sort of generic?
No, okay, so this was a weak event. What was, because I read the paper that talked about. So what was interesting is, I mean, the way it seems Fermi is set up, there are a whole lot of detectors that are sensitive. They call them different names, which means nothing to me, but I think it's that they're sensitive at different frequencies. So you get different frequencies at gamma rays. And what was interesting, although none of the actual detectors showed anything particularly high, it was that a whole lot of them showed things at exactly the same time. And that seemed to be from the point of view of the experimental team, another reason why they regarded this as due to a real source. Then you have a whole lot of discussion in the paper about whether the real source is actually a lightning strike somewhere on Earth, or which is also apparently sources of these things. But they concluded not to that.
This is a small question because
It's on.
my understanding is that event horizon can only be seen indirectly by infalling matter, at least. But here, I don't see the two things are spiraling, and the controversy seems to have started on event horizons. I don't follow. Can you explain? How can you see event horizon this way? You know, you cannot see event horizon.
No.
Only guess by infalling matter.
No, you can't see event horizon. All you can say is that the mathematical model, if you take two black holes, and compute two black holes within general relativity, and compute what happens, what you get out is a waveform that's very close to what is observed. That's all you can say.
But there seems to have started a controversy about event horizons. You flashed a title in the paper.
Okay, that is
Accurate.
okay. So that paper was saying that some people have said that quasi-nominal mode observed by the gravitational wave event showed that the final body must have been a black hole, and they were arguing with that. And actually, I don't think that the LIGO team claimed more than that you have this consistency. And in terms of the data that LIGO has, it's not a strong case yet that it must be a black hole, but one would need a stronger signal.
So my first question is that the gravitational wave, what kind of polarization it has, whether it is circularly polarized or linearly polarized?
The problem is that the polarization is not measured. Okay, in order to measure a polarization, you would need, to measure it properly, you really need something in you need two things in 3 dimensions. Okay, so it's not measured.
So what can we say about it?
From a measurement point of view, you can't say anything.
There are two polarizations like the electromagnetic wave. Which one we are not measuring?
Yeah.
You won't be able to
We can measure that.
But also the polarization is very much observable. You just have to move your coordinates or move the detector around and you get different polarizations. What does happen, what I can tell you is that something like this, the two polarizations are of equal magnitude but out of phase. So that the amplitude of the total gravitational wave field just varies slowly with time, it doesn't oscillate.
My second question is that the fact that gravitational waves exist, there was indirect evidence already, the indirect evidence was already there in 1974.
Yes.
So there were two quasars, and if one assumes that there is gravitational wave, then they calculated the time period, and that exactly matched with the experimental value.
Correct.
But now here in this case, the direct evidence has been made, but my question is that whether the indirect calculation has been done to check the direct evidence also.
Yeah,
Whether you
what do you mean the indirect? Look, what
is the thing which was done
the
for
pulse tail,
pulsars.
pulsar.
That's it.
Yeah,
Can we
and-
do the same thing in this case also for two black holes?
Yes, that's what the numerical calculation is all about. That's what these. That's what this is. This is the reconstructed model.
But for pulsars, there is a slowing down.
Yeah.
Slowing down of this.
Yes.
That is what they are doing.
No. The pulsars, the orbital period is speeding up. And
In spiral.
it's in spiral. The frequency is going up, so the time for each orbit is getting shorter and shorter. I can't remember by how much. And actually, the Hulse-Taylor that is now enormously more accurate. There are other double pulsar systems that have been seen which demonstrate the effect of much higher accuracy. So yes, that's all there. The trouble is that those systems are emitting gravitational waves at a frequency of the order of, I think, hours or at most minutes. And LIGO can't see anything below about 20 times a second. So although we know these events are there, LIGO can't measure them. It's the wrong frequency.
I have a question. So my question is there any estimate of the rate of events like these or stronger based on current models?
Yes, there are estimates, but they're extremely uncertain. You've got between sort of minimum and maximum is a factor of over 100. So particularly for black holes, there's little there's considerable uncertainty as to what the population of black holes is.
But basically, my question is how often can we expect to see events like these? How often? How many times? How many years?
How many times per year?
Generally,
How many times
so
per
like
year?
one thing they say is that once you start this, one expects about a few events in a year.
Yeah, yeah. You mentioned
That's sort of
That-
it.
Yeah,
But if
but
that,
is
if you
Yeah.
go to the.
But if there is if it's a 100 factor, it could be
Yeah.
a few events in a
Yeah.
lifetime.
No, if let me on. When LIGO reaches design sensitivity, the most pessimistic estimate will be more than one event per year.
Okay.
That's right, more than one year.
The advanced LIGO, from the
Yes.
advanced LIGO.
When it reaches full sensitivity,
Full sensitivity.
it's most pessimistic.
Yeah.
If it is a neutron star colliding, then there will be electromagnetic,
Yes.
lot of electromagnetic radiation first, and then gravitational. I mean, here it is weak, and that weak gamma ray probably giving us 10 to the power minus 5 M-sun accretion disk.
Yes.
The accretion disk is very, but in neutron star case, accretion disk is very strong. So
Yes.
we'll have lot of rich,
No, with the advanced
rich
like-
phenomena, right?
Yeah, with
Yes.
advanced LIGO, it was mentioned that they may be able to even find much smaller mergers, like even supernova,
Yeah,
pulsations,
some
where
supernova.
neutrinos also will come simultaneously.
Yes, I mean, that's certainly another target. Supernovas and neutron star mergers, and neutron star black hole mergers.
I'm just curious about this terminology. I mean, right now the status of LIGO is that it's advanced LIGO, is it not?
Yes.
And earlier we had LIGO 2 and then prior to that was LIGO 1, is that
Yes.
correct?
Yes.
Now, I don't know, this is probably not a right question, but just in brief layman terms, what is advanced mean?
It's really to do with it's
Kilometers.
one of the factors is that it was okay. So what advanced means is so it comes down to what the sources of error are. Right. So first of all, the first LIGO didn't have anything like 100 kilowatts circuit. I mean, it was the same design. I don't know what the power was, but it was nothing like 100 kilowatts. The second factor is these masses at the end. The real source of noise you have is vibrations, physical vibrations. I mean, which come all the time due to, even if you remove human activity just due to earth movements. You can't build these things too close to the sea because the wave, even that has some effect. So it's the isolation, it's the technology of isolation. These mirrors, I think, are something like 50 kilos each, supported by a single strand through. Yeah.
Also squeeze state stuff like that. I think
Yes.
photon shot noise was
Yeah.
brought down using the
Yes.
squeeze state
Yes.
radiation.
Yeah. So it's all these technological improvements.
Thank you very much.
Okay, that's.
So, one thing is bothering me about this, which is, it seems that this detection is very good in telling you things that you would expect to see.
Yeah.
But for events that you actually can't model right now, we don't know about. Like you mentioned, it's a window into the unknown.
Yes.
I don't see any way in which we can tell what the signal actually means. I mean, it's very good for things that we actually know how to detect. So we can say that, okay, this is 99.999% this event. But what if we see something extremely peculiar, in which case, I mean, how do we make sense of that in this context?
No, well, look, I think the first thing is, it's just as well the first thing we've seen is something that we know
Yeah.
about, because the first thing that one wants to do is really to validate the equipment. Once one is, in a way, confident that one has good equipment and good ways of analysing the data. There's some things that are strong signal to noise ratio. No, we just have to take it and do our best with it. All right.
All I wanted to make a comment was that for burst sources, there are wavelet analysis and other techniques
Yes.
in the frequency and time domain,
Yes.
so that even unknown sources can be picked up.
There is, I just want to make
Last comment, please.
something to the Indian context, that this bring down thing you see, this was the work done by Visweswara in 1971. Quasi-normal mode. And it is amazing to see that it exactly matches this. So it almost looks like it. And second thing is that in this paper, which you have about 1,000 the author, there are about 50
Indian
people of Indian origin.
50 plus or minus 5.
Yeah.